Hi there, Professor. So it's quiet night at work, so I thought I'd do this last experiment right now, and hope the guys don't interrupt. So, safety for this one, didn't have to do any SDSs, as we know, no chemicals needed. However, I did use my safety glasses from work. They're a shade 3 welding tint because I work on a weld floor. And I thought those would be better than just regular old safety glasses, and I made sure no one was around. I locked myself in a room so that no one would get lasers pointed in their eyes. That was about it for my safety results. It took me a second to realize what I was looking at when I flashed the flashlight and the laser both onto the CD. I noticed that I couldn't see the spectrum at first until I hit that special angle, which is actually in the definition of deflection for the spectrum. It needs to be seen at an angle and with the sun behind you, or the light source behind you, so that you can see that spectrum. My spectrum that I didn't bring in here with me, but I do have it written down. I did the colored pencil thing, and for the flashlight, from the center moving to the outer edge, I observed violet, dark blue, light green, orange, and red, which makes sense because it's a white light, and it acts as if you were seeing a rainbow, and you see all that visible light on the spectrum. Excuse me. Now, when it comes to the laser, I saw kind of a montage of colors. It was kind of crazy. As you took the CD and you kind of moved it a little bit from side to side, it would go from bright red to dark blue, and then if you turn it to a certain spot, then you would kind of hit all the colors in the spectrum again of visible light, and it was kind of wicked looking. And then I even got like a fanned out spectrum that was bright yellow in the middle, and then I kind of had violet on the side, and some blue and some red kind of skirting the top a little bit. It was pretty interesting seeing that. Now, when I did the laser through the diffraction grating, I did as the lab said. I set the diffractor up 20 centimeters from the wall. I used a wall because when I tried it on the box, my outside dots, they were too big, so they were falling off my box. So I ended up doing it on a wall, set it up to where it was 20 centimeters from the wall, and then I shined my light through, and I did notice that it did not matter how close the laser was to the diffraction grating or away from it. As long as I was centered on that, my points on the wall never varied in distance. And I found that interesting. So when I did my equation, I had 1 millimeter at 1,000 lines, which equaled 0.001 millimeters. And then when I plugged that into the equation, I got 666 nanometers of all numbers, because it fell in line with dark red on the spectrum scale. And yes, the wavelength was consistent with what I was expecting. I expected the laser to fall in that low energy side of the spectrum. And the white light, when I tried to shine it through the flashlight, when I tried to shine it through the diffraction grating, all it did was cast a shadow. I got nothing out of it. Cast a shadow of the frame of the diffraction grating, and that's all I got. I saw no discernible points. I saw no discernible spectrum colors of any sort. And so on to the most useful in supporting your understanding of the content. Now, I didn't know if they were talking about the content in the class altogether or the content in this. So I just kind of went with a general answer. I'm very much a visual learner. I can read something out of a book, and unless I have something to compare it to visually, I'm kind of lost. If I were to just read it out of the book and just leave it at that, it's kind of hard for me to grasp the concept, the theory behind it. So I liked it when we were doing the experiments, because then I could see what we were reading out of the book from the class and see how it actually worked and came together. It kind of clicked in my head a little bit more. Most useful, supporting the growth in the lab techniques and safety and chemical safety. I'm a safety person and at work, and I deal with SDSs all the time, so that was no shocker to me what was in an SDS. So that was kind of that wasn't very useful to me. However, learning about the different measuring devices, the cylinders, the pipettes, the beakers, you can go down to the teaspoons, how you can, and the scale, how to measure out the proper amount of chemicals and whatnot to get your reaction. However, there was a couple of times in some of the experiments that just never worked out for me, and I'm sure I had a few errors in that if I had done better, it would have done better. The least useful, I'm one of those people that you give me information out of a book written by experts, I don't find anything least useful. So I take it all in, and I honestly did not find anything in this class that was not useful for me in some way. Oh yeah, present the properly formatted graph from table 2. This here is the rate of decay from my Skittles experiment. So down across the bottom, I had the trials. On the sides here, I had the count of the decay as it went down. So trial 1, I had 100. At 0, at 0, I had 100. And then at 1, I still had 100. And sorry about that, my radio's still on. And as I started going throughout the trials, it only took me 5 trials to get down to 0. And well, I was at 4 at 0, and then on number 6, I guess I got down to 0. So there's my rate of decay for that second experiment, which was kind of interesting. I wondered all along what we were using the Skittles for, and it only makes sense that we weren't allowed to eat them, because would we have eaten the sodium chloride or the potassium chloride or the other chemicals? So treat it the same, right? Anyways, Professor, I'm sorry I let you down a few times throughout this term. I've been going through a lot with my dad retiring and trying to get him moved to Alabama, but it's been a pleasure, and it's been fun. You have a good day.